So I will start with the introduction to heat transfer, and then we will talk about the different mechanisms of the heat transfer. And this lecture is, the summary of the heat transfer textbook. Okay, this is the summary, but as we move on to the next chapters, you will see that we will talk about more detailed about each of the concepts of the heat transfer that we are talking now. The first is that the roadmap, as always, we have tried to do for all of the courses till now for the fluid mechanics, thermodynamics, and now for the heat transfer. So that the book that we are using is that Heat and the Mass Transfer by the Chengel and the Gajar, the latest edition. And there are about 15 chapters in the book, and we will see most of them. The first one will be that introduction. This is the lecture for today. And then we'll talk about the heat conduction equation, and this is a differential equation that we are going to solve it with the different initial and the boundary conditions. And then we will have the steady heat conduction. So this will be the next part. So you will see that this one is a simplified version of the previous one. So the equation that we are having here, so just 1 minute that I am regulating the pen here. Okay, so that this one is the general, and this is a differential equation. And this differential equation will be simplified to a steady form, and where you don't have a change in versus time, so the time changes are 0. And then we'll consider a bit more difficult case where you have the change in with respect to time. And then we'll use some numerical methods to solve heat conduction problems. And here you can use any software. I will use you can use the Excel, or that we can use the ease. And then we will have the external forced convection. This will be the next chapter. And then internal forced convection. Natural convection, it's also called the free convection. You can see that this part is the convection part, and this part is the conduction part. And then boiling and the condensation unit, and this one will be that phase change processes here. And the heat exchangers, and this one is very important part of the heat transfer, where you have the application of it. Okay. Application of the heat transfer is built on this heat exchangers. Then I'll tell that is the thermal radiation. This is the last part. And we will also have the lab sessions. I don't know how it will be designed, or I can show you the videos of the labs, and you can prepare the report. It is also possible, or I can give you the lab results. You can prepare the report, but at the end we'll have the lab sessions. Okay, we will have it. Okay, so that one way is that I can share the recordings with you, and you will prepare the report, or I can give you the paper form or the pictures or the photos of the lab sessions, and you will prepare report. For all of these cases, you have to prepare report. You will read the lab manual that I will send you, and from that lab manual, you have to prepare some theoretical part and calculation parts using the results that I have given to you. Here you will have the results. I will give you the results, and you'll make a lab report from those results. And the different lab sessions we have, the heat conduction of building materials, you will look for the materials that are used in construction, and then the linear and the radial heat conduction in metals, and heat conduction in gases and the liquids. And then you'll have the free and the forced convection unit, boiling unit, and the condensation unit. You can see that these lab sessions are in accordance with the chapters that we are seeing here. Here, for example, boiling and the heat condensation unit, you can see we have 2 lab sessions here. Free and the forced convection unit, so we have also the lab session here. Shell and the tube heat exchanger, and the jacketed vessel heat exchanger, and the cross-flow heat exchanger, flat collector unit, and this one is the solar collector, and evacuated tube collector, and this one is also the solar collector. This part of the lab sessions are the heat exchanger part, you can see. And the free convection part and the thermal radiation, which is the last topic, and as well as the last lab session. So if it is allowed that we can have the lab session at the university, we will do it. But if it is not, we will have the recordings or the paper forms that I will give to you with the results, and you will prepare the report for each of the lab sessions here. Of course, I will try to give more homeworks and in groups. Okay, this is more the homeworks, so that it will be that the 10%, okay, 10% of your overall grade. So these homeworks, as well as the lab sessions here. Okay. So that now I will start with the difference between the thermodynamics and the heat transfer. So in the last semester, we have seen the thermodynamics, and you will see that most of the concepts of the thermodynamics and the fluid mechanics are also used in heat transfer. But the laws of the thermodynamics are used in heat transfer, and the concepts of the thermodynamics are used in heat transfer. But the main difference between the thermodynamics and the heat transfer is that I will give you an example of the cooling of the hot coffee. We will do the thermodynamic analysis, and we can do the heat transfer analysis. If you do the thermodynamic analysis of the cooling of the hot coffee, say that I have a hot coffee at 60 degrees Celsius. And after some time, delta T, the temperature of the hot coffee drops to that is, let's say, 20 degrees Celsius. Okay. At the 60, so this one is I can take it as a closed system. If I'm doing thermodynamic analysis, it will be a closed system, and this is that system that I have here, and inside that system I have the coffee. Okay. What I can do is that I can write the energy balance, which is delta U is Q out, with a negative sign here. Delta is the negative Q out, because if you remember from the thermodynamics, you have the delta U is in minus out. For the system here, we don't have the in quantity, and therefore the property that is leaving the system is the heat only, and that is out property, and therefore you have the negative sign here. So I can find the internal energy at the initial state, U1, and U2 minus U1, and from here I can get the Q value here. What is the amount of the heat transfer during the process that the coffee is cooled in a time of the delta T? Okay, this is the thermodynamic analysis. But when you do the heat transfer analysis, it is more complicated, and here you will use the differential equations. What is the concept here? In thermodynamic analysis, you see that I have found the total Q out. This one is the total. Okay, but it is not possible to see here the variation of temperature. I cannot see it. Let me just write it here. Okay, so what I want is that, for example, so let's say that the first one, I want the variation of the temperature with time. Okay, you cannot do this one with the thermodynamic analysis, but if you do it with the heat transfer analysis, you can find that, for example, I don't know that, but let's say that it is dropping with an exponential manner. This one will get from the heat transfer analysis. Or what you will get is that second one, okay, rate of heat transfer. Okay. For the thermodynamic analysis, I have found that at the end of the process, delta T, the time here, I don't know what the time may be. For example, it can be that 5 minutes. After 5 minutes, I have this amount of the heat transfer. This is the total. But for the heat transfer analysis, I can find the rate of heat transfer. What it means is that in 1 second, so what is the value of the Q dot? Okay. In second 2, okay, in time is 2 seconds, what is the value of Q dot? Similar to heat transfer, the temperature variation here, I can look for the variation of the heat Q, heat flow. Heat flow from the system. It has the unit of watt by, it has the unit of joules by second. Joules by second, or it is the watt. You can see at 1 second how much. Say that at the beginning it is too high and then it drops. Okay. But for the thermodynamic analysis, you cannot do it. What you can do is that for the thermodynamic analysis, you can divide the Q out by delta T. Okay, but you can find that Q dot. But this Q dot is the average Q dot. Because at the end of the process, you have found that overall Q out divided by delta T, this will be average. But for heat transfer analysis, I'm not finding the average value. What I'm trying to find is that I can find the Q dot versus time. At the first second, what is the amount of the heat transfer. At the second, what is the amount of heat transfer. And at each time, I can see what is the amount of the heat transfer that is removed from this coffee. You can see that this is the main difference. The thermodynamic analysis is concentrated on the amount, and heat transfer is on the rate. And the one more difference between the thermodynamic analysis and the heat transfer is that here you are dealing with equilibrium, but here you have the non-equilibrium. So equilibrium, if you remember from the previous semester, that for example here you have the 60 degrees Celsius, this one, 60 degrees Celsius. What you are doing in thermodynamics is that it is in equilibrium. Equilibrium means that if I take the coffee here you have the 6 degrees Celsius, here I have the 6 degrees Celsius, here I have the 6 degrees Celsius, or here 60 degrees Celsius. Anywhere, at any location, I have the 6 degrees Celsius. Okay. This is for the thermodynamic analysis. But for the heat transfer analysis, you don't have that simplification, but what you are doing is that you are looking at the rate or the non-equilibrium analysis. Okay, this is the first part. And the second part is that what is heat? Okay, the definition of the heat, you know that it is, in the past, the people were believing that heat is like a fluid. Okay, when the heat is removed from the body, the amount of the fluid in that body is decreasing. Okay, so that this is called caloric theory. You can read about it. Okay, this is a very important and very historic part of the heat, and where they are considering what is the definition of the heat. And so this one taken has, this one was about the 17th century. But later people believe that that heat is not like a fluid, and it is not conserved. It is not conserved property, and it is a type of energy transfer. This is the first definition of the heat transfer. Okay, and the caloric theory, I should say that this one is old. Okay, and wrong, old and wrong, but it's important. This is the type of the energy transfer. Okay, and the reason is delta T. What is heat transfer? Heat transfer is a type of energy transfer that happens due to temperature difference. Okay, but at the end you have to remember that it is energy. Okay. It is not like a fluid, as the people in the past said. This one says that fluid-like stir, fluid-like. It is not a fluid-like. It is not a fluid. It is not conserved. This one you should add it. This one is non-conserved. It is not a conserved property, okay. And it is a type of the energy transfer. Okay. And now application areas of the heat transfer. The first application area is that the calculation of heating and the cooling capacity of the, of the rooms, of the offices, or the markets, or so anywhere. If you are trying to build an air conditioning system, or if you are trying to put a heating system, and you have to know what is the amount of the cooling capacity of that air conditioner, heating capacity of the heating system. We have to find it, and to find it, we are using the thermodynamic, that is heat transfer. We can just give you one example. Say that you have a room. This one is, it can be office, for example. For the office, what you will have is that you will have one window, and you will have that walls, you will have the floor, and you will have that ceiling, or the roof. Okay, for the office building here, you have to find what is the heat loss from the window, Q dot. What is the heat loss from the walls, Q dot, from floor, and from the ceiling, or the roof. You have to find all of the heat losses. These are the heat loss. Yeah, from the office room. Okay, so you have to calculate all of it. And how do you calculate it? You are calculating by using the equations of the heat transfer. Okay, and then after finding this total amount of the heat transfer, and you are determining the amount of the air conditioning unit that you will need, or if you are using the heating system, and that you have to find what is the amount of the heating system and how many of them do I need after this calculation process. And very is the application area of the heat transfer. Or the finite systems. This is also another important concept and is also used for cooling. I can show you just some examples of the finite systems. You can see that fins here. These are the additional surfaces. So the surfaces that you are adding to the system to increase its surface area. We have added it. You can see here, you have the fins here. These are the fins, and there can be different types of the surfaces that you are adding. It can be rectangular, it can be triangular, trapezoidal, circular. Okay, there are different types of the fin systems. What you are doing is that you are adding these fins, and by the addition of the fins, you are increasing the surface area. Increase surface area, and by increasing surface area, and you have the removal of that Q dot increases. Okay. For example, for the engine here, you can have the temperature of 700 degrees Celsius. At this temperature, 700 degrees Celsius, it is too high. And to remove this amount of the temperature, this amount of the heat from the engine, you will need high surface area, because the surface area that you are having here is very small. What you are adding is that you are adding additional surfaces. Additional surfaces to increase the amount of the surface area and then help the removal of the Q. Okay, that is the condenser of the air conditioner refrigerator. And this condenser, again, you can use, it uses the fins. And the cooling of the electronic components, this is also the application of the heat transfer. You will see that we will have the PCBs where we use the natural convection concepts to determine the amount of the heat transfer that is needed. And also at the end, you have to place some fan, and to place the fan, you have to know what is the heat removal from the system. Heat exchangers, this is also a very important application area of the heat transfer, and here I can just give you one example, which is the radiator of car. Okay. Or you can see this one is the condenser. This is the heat transfer, or you can see the one here. So all of these devices are the application area of the heat transfer, and we'll calculate some examples on the condenser and on the radiator and also PCB, etc. And the thermal ablation, and this is just one example of the biomechanical application of the heat transfer. And for the biomechanical application of the heat transfer here, so this is used in the cancer. Okay, that you have the cancer therapy, and here we are using this thermal ablation. How it works, and they say that you have a cell, something like this one. This is the cell of your body, and inside this cell, you say that you have the tumor here. Okay, tumor means that this is the cancerous. Okay, there is a cancer on this part of the cell. Okay. So what you are doing in thermal ablation is that you are, so you are injecting sphere. Okay, these spheres are the ferromagnetic. Okay, you are injecting the ferromagnetic sphere inside that tumor. Okay, so that the sphere is maybe at the size of the tumor, or it can be less than that one. But at the end, you are injecting the sphere inside that tumor. And what you are doing is that since it is ferromagnetic, and you are heating this sphere. Okay, then what you are doing later is that, so that heat that sphere. Okay, this heating process is that non-invasive. Okay, you are heating from outside of the body, human body. And when you heat this sphere, it burns this tumor. Okay. As it burns this tumor, and it is, that you are that this is the cancer therapy, as you are that burning this tumor, and it ends the illness. But the problem here is that when you heat this sphere, the temperature here around the sphere, around this, for example, radius, or around this radius. Okay. So that because from this source you have the heat. You have the heat. Okay. If this heat is very high, Okay, what you can do is that at the high amount of that heat, so if Q dot is high, okay, what you will have is that the temperature is high. If the temperature is high, what you will do is that you will burn the healthy cell. Okay. You will burn the healthy part of the cell, but your aim is not the cell itself, your aim is this tumor. Therefore, you have to regulate the heat transfer such that it only works around this tumor. Okay. It doesn't, that burn the cell which is healthy around this tumor. This is the application of the heat transfer, and for this, the thermal ablation, you will have the homework. Okay, but at the end, this is one of the applications of the heat transfer, which is the biomechanical application. And the insulation, this is also used widely in industry. For example, we are using the insulation for the pipelines, so that we are using insulation for the heating systems, etc. Well, this insulation helps to prevent the heat transfer from that surface. And these insulation materials that we are selecting are the application area of the heat transfer. And the last part is the solar collectors. And as for the solar collectors, we'll have the homework and we'll have the lab session. Okay. And there are different types of the solar collectors. At the end, they are the heat exchanger. Yeah. By this heat exchanger, at the end you should remember that this is a heat exchanger, okay, heat. This is not the solar panel, okay. The solar panel, this one is different. Here you are getting electricity. You are getting the heat. Okay. Now I will review the thermodynamics and the fluid mechanics a little bit, because if you will use it in the concepts of the heat transfer, and you have to remember it. Okay, so firstly, we'll start with the internal energy. For the internal energy, if you remember, it was the sum of the molecular energies. So there are different types of the molecular energies. It can be due to chemical bonding, it can be due to the nuclear part, and the kinetic part of the molecules, potential parts of the molecules. At the end, the sum of the molecular energies, since it can be the kinetic, potential, bonding, etc. At the end, we have the one type of the energy, which is internal energy. Okay. We are showing this one as the U. And if it is, or it was the U, which means that the capital case U divided by the mass of the substance or the material. This one was from the thermodynamics, and here I will add the one thing here is that the internal energy can be in the form of the sensible heat, or it can be in the form of the latent heat. Okay, what it means is that for the sensible heat, as the name says, it is sensible. Okay, when you heat, okay, that when you heat material, okay, let me start from the beginning. When you heat the material, its internal energy increases. Okay? And this internal energy increase is shown as a temperature increase. This is very easy one. And for example, if you heat any metal substance, you will increase its internal energy and as well as its temperature. This is called the sensible heat. But for the latent heat, what you are doing is that you are doing the same process, and you heat the material, or you heat the fluid or material, it doesn't matter at the end. You are increasing the internal energy of the material, but the temperature doesn't increase. Temperature remains constant. This is called the latent. And latent, this term means that hidden. You are adding the heat, but the manifestation of that heat addition is not in the form of temperature, but is in the form of the internal energy. You can give me one example for the latent heat. And just give me one example where you heat the material, the temperature doesn't change, but its internal energy increases. But boiling. Okay. So that boiling is latent heat, because when you heat water, so what happens? The temperature is constant, which is 100 degrees Celsius, but the internal energy of the water increases. Okay. So can you give one more example where you have the latent heat? But the opposite of the boiling where you have the condensation. Okay. Again, you have this process. Or I can give you one more example, which is very familiar to you. Evaporation. Okay. Evaporation happens, for example, our body. Okay. Temperature remains the same. That is the 37 degrees Celsius. This is, I can give you that evaporation. But we feel cold. Okay. So just one example can be that fan or ventilation. Okay. When you use the fan in summer, when you use the fan, you feel cold, but your body temperature is constant, 37 degrees Celsius. The temperature doesn't change. But what happens is that evaporation. You are losing the internal energy. You are losing energy, but the temperature is constant. So anyway, that is, generally we can summarize them as phase change processes. One more example can be that melting. When you melt the material, it melts at a constant temperature, but its energy decreases. Sorry, that increases. This is the internal energy, and I've said it, sensible, and the other kind can be that latent heat. Refrigerator. What do you mean by refrigerator, my friend? So that enthalpy. So that enthalpy is, if you remember it, it was a combination property, and where you call it as that internal energy and plus that energy that is required to, that maintain the flow. This one is that the flow energy to flow, and this one is that internal energy. So when the fluid flows, you will have that some energy to flow. You will need it due to pressure. It will have some pressure, and it will displace some specific. It is very similar to that is boundary work. It will need some pressure. It will need some that is specific volume, and then you will have some internal energy. This is called the enthalpy. Okay, so the next is that first law of the thermodynamics. I will look for first the closed systems and then for the steady flow systems. Okay, for the closed systems, that if you remember the first law, it was saying that the delta U is equal to a total in minus total out. If it is closed, this one can be by heat, it can be by work. And the second one will be that 3b. Here I'll talk about the steady flow systems. That's systems that not change with respect to time, and this one is that open systems. For example, the pipe. Okay, I have a pipe here, and the fluid enters into that pipe. Fluid leaves that pipe here. So you will have the one here. You will have the two property here. And for this one, you will have the in properties are the same as out properties. Okay. This one, you should remember that it is steady. Okay. And the in property can be, for example, internal energy at inlet, kinetic energy at inlet, potential energy at inlet, and that one will be enthalpy at outlet, kinetic energy at outlet, and the potential energy at outlet. If you are adding, for example, some heat to that system, say that you are adding some heat here, Q. So this one is the Q, not the Q dot. This one should be lowercase q, heat. Okay, if you are adding the heat to the system, let me select my control volume here. Okay, and then you will have this, since it is addition, so it will be that Q here. Okay, this is for the steady. If it is unsteady, then you will have the change of internal energy. So that if it is unsteady, you remember it, unsteady systems are more complicated. Okay, unsteady but uniform flow. So that for unsteady uniform flow properties, what you will have is that delta U will be equal to that M2 and the properties at 2 minus M1 So I can just write this one as, again, in minus out, but this time it will be that in minus out. This time you will have the change in internal energy of the system. This is unsteady, but most of the time, since we are looking at the steady cases, then there is no problem that we are dealing with this process here. Okay, so then the conservation of the mass, that this one says that the m dot is constant for steady flows. Okay, so this one is the general case. The general case says that rho a v is constant. Rho is the density, a is the cross-sectional area, and the v is the velocity. And this multiplication of the terms are constant. This one is for steady flow. But if I have this is general case, okay? But for liquids, okay, liquids is the special case. You can just write that A and the V is constant for the liquids because that the density doesn't change, so that incompressible. Okay, but this part is general, so this is true for air or liquid. This is true air or liquid, but for the special case where you have incompressible, the density is constant. Then the rho term drops out, and you will have that cross-sectional area multiplied with the velocity of the substance is constant. And the last part is the energy balance at interface. This is the very important concept that we will use in heat transfer. What is the energy balance at interface? Let me talk about that one and finish. Okay, so that interface is that. So let me give you just one example as the pipeline here. So I will take, or let's say coffee. Okay, this is the coffee glass that you will have here. And inside that coffee glass, you will have, let's say, how much temperature? 50 degrees Celsius. Okay, and interface, just let me add it here. Interface means that it is very thin. So very thin means that no thickness. Okay, and no thickness means that no volume. No volume means that it cannot store energy. Okay, and then you can see that it doesn't have any volume. Since it doesn't have any volume, then it cannot store energy. To store energy, you will need some geometric body. But here there is no any geometric body. It is very thin and no thickness, and it cannot store energy. So that, in that case, for example, I can take this part of the as interface glass. This is the interface. Okay. This interface is the part that I'm interested in. And into that interface, I have the, so let me just take it out and zoom in. Okay, when you zoom in, you will just see a line. And you will not have a, that three-dimensional body. It will be line. This one is line. And into that interface, since this one, the coffee is at 50 degrees Celsius, and the environment is at, for example, 20 degrees Celsius. And from that interface, you will have the heat transfer. This one is from, this part is a 50. This one is 20 degrees Celsius. You will have heat transfer from the coffee here, and that heat transfer will leave the interface here. This one, let's say that Q dot 1, and this one is Q dot 2. And the Q dot 1 will be same as Q dot 2. And it is also possible that you will have that Q dot 2 here, or you may have one more heat transfer here. For example, it can be that it will be Q dot 3, and it will have this Q dot 2 plus Q dot 3. You can see that heat transfer comes from the coffee to the interface here. Since this interface doesn't have any volume, it cannot store energy. Whatever comes to that interface, it leaves the system. Okay, it has the Q dot 1 into the interface, and then it leaves as Q dot 2 plus Q dot 3. It can be Q dot 2 plus Q dot 3 plus Q dot 4. It doesn't matter at the end. This one has a steady. This is like a steady flow system. You have in and out is the same. So this one has that in same as out. Okay. This one is also a very important concept that we will use in the analysis of the heat transfer problems. Okay. Good. So here we have a simple example for the review of the thermodynamics and the fluid mechanics. This one is a very simple example, but to summarize what we have talked in our previous slides, let's do it. So we have the aluminum rods with a density of 2647 kilograms per meter cube and a specific heat value of 1.022 kilojoules per kilogram Kelvin is being sent through an oven. So that I have an oven here. This is the oven. This oven is hot, and I have the aluminum rods here. These are the aluminum rods. So that. And from that oven, what I'm having is that you are having heat transfer Q. So aluminum rods, so with the density is given, specific heat capacity is given, and during the heat treatment process, when you have the heat treatment to this aluminum, you can use for any purpose. For example, you can draw the aluminum rods to make it thinner. It is not a problem here. Here there is the values. The temperature of the rods increase from 25 degrees Celsius to 540 degrees Celsius. And the rods are drawn with a speed of 5 meters per minute. Determine the rate of heat transfer if the diameter of the rods is 4 centimeters. This is the question that we need to answer. What is the rate of heat transfer if the diameter of the rods is 4 centimeters? Okay, now let me just write the values here. At the inlet here, this one is the aluminum rod. Here I have the temperature as 25 degrees Celsius. Here I have the temperature of 540 degrees Celsius. And the rho of the aluminum is given as 2647 kilograms per meter cube. And the Cp value is given as 1.022 kilojoules per kilogram cube. Okay, and the rate of it, that is, in 1 minute, you will have 5 meters. So when you have 1 minute, 5 meters of the rods are transferred through the oven. Determine the rate of heat transfer, rate. Okay, this one is the rate. So let's solve it. You will first solve as a closed system. Okay, and for 1 minute. For 1 minute. Okay. This is my rod here. Okay, and has a length of 5 meters. Because I'm dealing with 1 minute. Okay, in 1 minute I have the 5 meters that is heat transferred, and the cross-sectional area is constant. It's 5 centimeters. Sorry, the 4 centimeters. Okay. And now I will write the first law. If you go back to here, closed system, delta U is Q minus in minus out. And for this system, there is no work. There is only in, which is heat, and delta U. So I will just write it as delta U is equal to Q. Okay. And here, delta U is, instead of that one, I can just write mCp delta T. So how do I write it? So that here you will have the approximations. The first approximation is that Cp doesn't change with temperature. Okay, this actually, there is one approximation here. Cp doesn't change with temperature. Okay. And then if I just write it, instead of mass, I will just write, this one is the density into volume. Okay. And instead of volume, cross-sectional area into the length. So it will be that the rho into cross-sectional area into the length. This will be the volume part into Cp into T final minus T initial will be equal to Q in. And just write the values here. Final temperature is 540. Initial temperature is 25. Cp value is 1.022. L value is 5. Density value is 2647. AC value is pi d squared by 4. And here the diameter value is 5 times 10 to the power of negative 2 meters. Okay, so I will give you some time to calculate this Q in, and then I will move on to another method to solve the problem. So Q in, you will find approximately it will be 8757 kilojoules. This will be Q in. But as I said, we are analyzing for 1 minute. But if you are trying to find what is the Q dot in, a rate of heat transfer, and then you will divide that Q in by 60 seconds. Okay, 146 kilowatt. That is as an analysis of the closed system. Okay. But you can do this analysis in a much more simplified manner, and if you do this as a control volume analysis. Okay. In that case, you will have the very simple relationship, which will be that Q dot will be equal to M dot Cp and the delta T. Okay. And instead of M dot, you will just write that rho A and the velocity and the Cp by delta T. The velocity here, it is given in the question, it is given as 5 meters per minute. So 5 meters per minute. And you have to convert it into seconds. Okay. It will be that 1 minute divided by 60 seconds. And then the cross-sectional area, the same one here, pi d squared by 4. The density here, the same, 26, 47. And the specific heat value, which is 1.022. And delta T value is 540 minus 25. And if you do this calculation here, you will get 146 kilowatts. And see, it is the same value. Same value if you do this one as a closed system for 1 minute and divide by the seconds, or you are doing this one as a control volume analysis. There's a flow of the rods from our system. During that flow of the rod, this is that the fixed rod and the fixed mass actually, and here you will have this 5 meters per minute as the velocity, and if you do this calculation, you'll get the same answer as the previous one. Now comes the heat transfer, and for the heat transfer, we will first start with the modes of heat transfer. And the modes of heat transfer means that there are the mechanisms. You can see the mechanisms of heat transfer, or the types of heat transfer. There are different types of the heat transfer, and I will just start with the first. I will just write the names. First one is the conduction heat transfer. Heat transfer that happens by conduction. And I will have the convection heat transfer that happens by the fluid or the substance flow. And the last one is that radiation. Okay. This conduction, convection, and radiation, here we are, talking about the summary of them. But in our next chapters, you will see that, for example, there are 4 chapters about conduction, there are 4 chapters about convection, and 2 chapters about radiation. Okay. These are more developed topics, but here we are doing just a small summary, and we are trying to understand what we mean by conduction, what we mean by convection and radiation. Okay, this conduction heat transfer, it can happen in gases, it can happen in the liquids, or it can happen in solids. In all of these fluids, it doesn't matter whether it is gas or liquid or solid. There is one consideration that the equation is the same. It doesn't matter. The equation is the same, but the mechanism, the amount of heat transfer is different. But you should remember that if it is gas or liquid, it should be stationary. It cannot move. If it moves, then it will not be convection, it will be convection, the second one. Okay, now firstly, I will just write the equations for the, we will write the equation for the conduction, and I will show this conduction as the Q dot CD. Okay, CD means conduction, and the Q dot is the conduction heat transfer. Now we are trying to derive what is that Q dot CD equal to. Okay, I will just give you examples of this. That the examples for the conduction heat transfer and varying each parameter at the same time, and we'll try to understand what is this equation equal to. First one, in all of these cases, I will cover the wall, so that, and the wall. This one is there. And in B case, it will be also the wall. I have a wall here. This can be the wall of a room. It doesn't matter. So the wall of the room here. Okay. And in one side of the wall, you have, let's say, 25 degrees Celsius. On the other side, you have 10 degrees Celsius. Okay. In the B case, the same wall, the same material, we don't change anything here. Here you have the temperature of 25 degrees Celsius, and here you have the temperature of 0 degrees Celsius. And my question is to you, in which case the heat transfer is more, in A or B? You can just write as a comment here, in which case we have more heat transfer, in A or B. Okay, in B case, it will be more heat transfer because the delta T is more. Here you have delta T more. Then the conduction heat transfer, you can see it is wall and it is stationary, it doesn't move. In the conduction heat transfer, the heat transfer itself is proportional to delta T. Okay. If you increase delta T, this one increases. If you drop delta T, this one drops. The second case, now I'm adding the second part here. I have the same wall here. Here the temperature is 25 degrees Celsius. Here temperature is 10 degrees Celsius. Okay. This is wall, and it is case A. In the case B, I have the same wall. Here I have varied the thickness of the wall, and I have the 25 degrees Celsius, I have 10 degrees Celsius. And this one has a thickness of, let's say, delta X1, and here I have the thickness of delta X2. So in which case we have more heat transfer, first or the A or B? Do you have more heat transfer, A or B? Heat transfer is more in A, okay? Then, so it is inversely proportional to delta X. If you increase the delta X, this one drops. If I decrease delta X, this one increases. Therefore, I should divide this one by delta X. Okay, this is the second part. And now let me add one more case here. Now let's think this wall as a three-dimensional. This is the part that we are seeing. This is into the page. And this one is also the into the page. So that is, there is heat transfer in that direction, which is Q. Dot. Okay, now I have the same wall here, the same height. So you have to think this one as a three-dimensional case. Okay, this is again the wall. Okay, this is the wall, the same wall. We don't change anything. What we are doing here is that we are just adding the dimensionality here. Just let me add it for the first case here, and okay, for the second case, I will do the same stuff here. It has the same thickness, same height, but the cross-sectional area is more. So the question will be, which one has Okay, so I have the thickness is the same, so everything is same. Okay, and the only difference is that here you have different cross-sectional area. So this one is a cross-sectional area 1, and this one is a cross-sectional area 2. So what do I mean by cross-sectional area is that into the page it has a dimension of L, and this one is a dimension of W. Okay, W2 and L2. So AC1 is W1, L1, and AC2 is W2 and L2. Okay. And in which case do we have more heat transfer, in A or in B? And I should add this one, that if it is not clear from the picture, AC2 is greater than AC1. More heat transfer, A or B. And what it means is that if you increase the cross-sectional area, then the heat transfer is increasing. But here, the one thing that you should always remember is that this AC is perpendicular to Q dot. Okay, you have to remember this part. Cross-sectional area should be perpendicular to the direction of the heat transfer. It is very important. So therefore, if you increase the cross-sectional area, then the heat transfer increases. And I will add the cross-sectional area term.